with the presentation or with the opening session. So this workshop will be recorded, or let's say at least most sessions will be recorded. So just that you are all aware of that. So I'd like to welcome you all to the 11th International Workshop on Human Behavior Understanding. So we were supposed to be at, as I said, at Hawaii at this point, but we will do it virtually this year, and hopefully if we repeat next year, then we are actually on Hawaii in a nicer location. So HBU is the 11th in this workshop series, and this year it's held as part of WACWI, and it's the first virtual workshop. So there were 5 organizers. So Abjit and Albert are here, both of them. Then we have Kyangji and Umpada Paul from the United States and India, and also Maria Ivanovska from our university was helping with as a web chair for the workshop. So we had quite let's say extensive program committee, 23 members who helped with the review of the papers that were submitted. And as you can see, we had representation from different continents, different universities, all with experience and expertise in human behavior understanding, computer vision, biometrics, and other areas that are relevant for the workshop. So we organized a reviewing procedure for the submissions that we received. This was overseen by the organizers, and the review was done by the 23 program committee members that we had. So in total, we received 11 submissions, and then at the end decided to accept 4 the highest quality papers for presentations. So from the submissions that we had to desk reject 2, but the rest was reviewed, and most of the submissions got 3 reviews. So there were 2 where we only had two reviews, but still let's say the feedback was very consistent. So we were able to make, let's say, informed decisions on all papers. So we also tried to discuss borderline papers separately, but there was just one case where we needed to make a final judgment and to re-examine the paper. The rest was pretty clear. So we also had 1 submission from one of the organizers, and that was handled separately. So the organizer that submitted didn't have access to the paper, to the reviews, so to keep the review procedure as objective as possible. So for the program of the workshops, I think we have a very interesting program, as you will see. We have 5 keynotes. So the first one will be from Professor Rachel Jack from the University of Glasgow. Then we have Mohamed Chetwani from Sorbonne University, Lisa Anthony from the University of Florida, Luis Philippe Morenzi for Carnegie Mellon University, and Sidney DeMello from the University of Colorado Boulder. And in their oral session, we have 4 papers, so the 4 that were accepted for presentation. Sorry. So as I said, the workshop will be virtual, and we will be using Zoom. So in between the presentations and the talks, if anybody has any questions, you are free to use the chat feature of Zoom, and the session chair will then read out the questions after the talk. So all presentations will be recorded, or let's say most of them. So we will not be able to record one of the last keynote talk, but the rest will be recorded. And just maybe some ground rules for Zoom, because this is virtual. We have to have some policies how to handle the logistics. So during the talks, please mute yourself and turn off the videos just to save some bandwidth for the speaker. So you can always post questions in the chat. So if you have questions in between the talk, and then once the presentation is over, we will have a live Q&A, but just to keep that organized, maybe try to use the raise hand feature of Zoom. So in the reactions button, you can see you can raise your hand, and then the session chair will give you the word, and you are free then to unmute yourself and maybe turn on video if you want, and then ask the question directly to the presenter. So there's a few session breaks also planned in between the talks, and we would like to have that as a sort of social thing, right? So some of us, it's pretty late here, will also have some sort of dinner in between during the breaks. Just maybe keep the channel open, turn on the video, and let's chat. I mean, we have a lot of topics that we can discuss, and just to have a social aspect to the workshop as well. Maybe let's try how that works out, right? Okay, before we start, we would also like to acknowledge our supporters. So the Slovenian Pattern Recognition Society helped us a bit with the website and support on our side. So whereas I'd like to start the workshop and give the word to Abhijit, who will chair the first keynote talk and also introduced our first keynote speaker. So let me just figure out where I can stop sharing my screen. Okay, I see. And I'll give the word with that to Abhijit to introduce our first speaker. I think you're muted, Abhijit.
Thank you, Vito. So I'll introduce our first keynote, Professor Rachel Jack. So Professor Jack is at the Institute of Neuroscience and Psychology from University of Glasgow, Scotland. Professor Jack's research is preserved on the significant advances and understanding on facial expressions of emotions across cultures, using novel interdisciplinary approach that combines psychopathy and social psychology, dynamics of 3D computer graphics, and mathematical psychology. Most notably, like Professor Jack, have worked on the relevance of cultural specific in facial expressions and emotions, that 4, not 6 expressive patterns are common across cultures and facial expression transmitted in the hierarchical over time. So Professor Jack is the recipient of several awards, including American Psychological Associations, New Investment Awards, and so on. And so Professor Jack is also like chair of the Association of Psychology of Science of International Committee. So without any delay, I will like hand over the session to Professor Jack and to continue with her keynote.
Okay, great. Thanks very much for that introduction. Thanks very much, everybody, for inviting me as well. It's really great to be here. It's really good to see familiar faces and see some new unfamiliar faces, especially when the other keynotes are so, kind of admirable. I know them all, and it's really exciting to be kind of listed amongst all of these other people. I'm also really looking forward to your thoughts and feedback on this work at the end of the talk. So I have recorded my talk. I'm just going to share my screen and then play the talk. If there's any problem during the talk, then just let me know. I'll make sure. Good morning, good afternoon, good evening. I'm Rachel Jack from the University of Glasgow, and today I'll be sharing with you some work from our lab on modelling dynamic facial expression behaviours using psychological science. Before I begin, special thanks to the organisers of this workshop for giving me the opportunity to share our work with you. It's also a great honour to be your opening keynote speaker. So, as some of you might know, I'm a psychologist, and my research focuses on understanding how humans interpret non-verbal behaviours, particularly facial expressions shown here, and how this varies across cultures. Specifically, our aim is to understand the language of non-verbal behaviour, that is, how individual face movements combine to create meaningful facial expressions, and their syntax, grammar, and semantics. And we have this goal because, unlike thousands of written and spoken languages, even ancient languages, we do not yet have a formal understanding of nonverbal languages, such as facial expressions, body postures, and hand gestures, those that we use every day and which are so critical to the functioning of human society. In turn, without this set of rules, we remain limited in our ability to equip digital agents and related technologies with the ability to generate nonverbal behaviors that will engage their human users effectively. And there's a very simple reason for this. It's because human nonverbal behavior is incredibly complex, comprising a huge number of different complex dynamic patterns of face movements alongside body, arm, and hand movements. So today we'll use the human face, which is just one of the tools used for social communication, to illustrate this point and outline one method from psychological science that we've developed that has made this complex task more tractable. And in doing so, I'd like to share with you a few main points that will hopefully better enable psychological science to play a role in informing the design of digital technologies that rely on an understanding of human behavior. So the first is that facial expressions are not universal. Universality is a commonly held assumption, but is in fact not true, and it never has been true. The second is that knowledge of facial expressions as a communication tool is currently quite limited, in part due to the use of traditional theory-driven approaches. And as mentioned before, these in turn have restricted the design of digital technologies and the ability of psychologists to play a leading role in their development. So let's start first with the common understanding that facial expressions are universal. So in developing technologies that can automatically detect or generate facial expressions, many have turned to the field of psychology to understand which specific face movements, such as smiling, frowning, or eye widening, correspond to different social messages, such as emotions. And in doing so, one will very quickly come across one of the most influential and well-known findings, that 6 specific facial expressions shown here universally represent the 6 basic emotions of happy, surprise, fear, disgust, anger, and sad. Specifically, this work, pioneered by Ekman and based on Darwin's work, took photographs of facial expressions such as these and showed them to people across the world, including Japan, the US, the UK, Papua New Guinea, and China, and asked them to classify these images by emotion, often using an alternative force choice task. It's also worth pointing out here that they used recognition or perception to understand facial expression production, because they reasoned that if facial expressions were recognized in a given culture, then they are likely to be produced in that culture. And Darwin, as an evolutionary biologist, first noted this intimate link between production and perception, stating that one of the leading principles which have determined the chief movements of expression is the recognition of expression. So in addition to this work and the many studies that followed, it was consistently reported that these facial expressions are recognized across all cultures. They then quickly became the gold standard in psychological research and in other fields such as affective computing and social robotics. Consequently, many automatic facial expression detection and generation technologies are based on these 6 universal facial expressions. However, there are several critical issues that limit their use in such applications. The first, as hinted at earlier, is that these facial expressions are not universally recognized across cultures, at least not in the way we might expect. In fact, extensive cross-cultural recognition studies, including Ekman's, have consistently shown that they elicit considerable variance in recognition accuracy across cultures. So to illustrate, here is a map showing the results of several key studies, including Ekman's seminal 1969 science paper, where each point represents the average recognition accuracy of each of the 6 emotions in that geographical region. Pinks and purples indicate high accuracy, blues and greens indicate low accuracy. Those outlined in black are those below 75%, which would be considered overall typical recognition performance using clinical references. And as you can see, recognition accuracy is generally higher in Western countries than it is in East Asian countries, with some levels falling quite low. This is particularly true for fear, disgust, and anger. Now, you might be thinking, if there are cultural differences, why were they reported as universally recognized? And the answer is quite simple. Most studies use above chance performance, which in a 6 AFC task is about 17%. So in using this rather liberal threshold, any substantial cultural differences were masked. Therefore, these robust results suggest that instead of being universal, these particular facial expressions represent those used in Western culture. Okay, so that's the first key point that I'd like to make today, that the 6 basic facial expressions are not universal, or not at least in the way that most of us would understand it. Now, these results raise a couple of questions and observations about our understanding of facial expressions. So this brings us to the next point I'd like to make today, which is that knowledge of facial expressions is currently quite limited, in part due to methodological limitations. And the good news is, as I'll show you today, that new technical and methodological advancements now overcome these limitations and enable us to broaden and deepen our understanding of facial expressions. Okay, so I've given you one example of how knowledge of facial expressions is currently limited, that we have a good representation of Western facial expressions, but less so of other cultures. There are also many other areas where knowledge needs to be built. For example, most research is focused on emotions. More specifically, it is focused on a small subset of only 6 emotions, when of course a much wider range of nuanced emotions exist. Then within that, as shown earlier, only a small and specific set of facial expressions have been tested. That is the 6 standardized images you saw earlier, which represents a very small proportion of all the facial expressions the human face can make. We also know that they were selected in a top-down manner by the experimenters. And finally, they are static, so they don't have any potentially important dynamic information, such as temporal sequencing of the face movements, their intensity, and so on. So together, these various methodological choices and research directions have limited knowledge of facial expressions. Now, why is that? And the answer, of course, is quite simple. It's because, as mentioned earlier, facial expressions are complex signals, a point that is summed up very nicely by Labar in 19, who said that in the language of gesture all over the world, there are varying mixtures of the physiologically conditioned response, so those which are cross-cultural, and the purely cultural one, so that is what is culture specific. And it is frequently difficult to analyze out and segregate the two. And this is as true now as it was then. So let's take a closer look at this complexity. So as most of you are aware, the human face is comprised of many different muscles that can each be activated independently at different intensities, accelerations, and so on, and combined in different ways to create a high number of complex dynamic patterns, which we call facial expressions. This complexity is, of course, a great design feature because it means that the human face can transmit a very wide range of nuanced social messages, including emotions, mental states, and behavioral intentions. And given their central importance in human social interactions, understanding them as a tool for social communication in terms of their grammar, syntax, and meaning has been a focus in psychology, anthropology, and philosophy for well over a century, and now more recently in computer science and social robotics. But as just illustrated, identifying amongst all of these complex variations which facial expressions convey which messages to whom is empirically very challenging, because the face is a high-dimensional dynamic information space comprising many individual face movements called action units, each with dynamic parameters, such as those shown here. So how do we tackle this complex task of finding, in amongst all of these various combinations, which ones transmit meaningful social messages? One approach, which we have developed in Glasgow, is to use the same classic method as traditional research of showing facial expressions to people and asking them to categorize these images, but with a psychophysical twist. So let me show you how this works. Okay, so imagine that you see this person. You might think that they are disgusted or angry. Now, how about this person? Well, it's not really clear how they feel. At least it's not very clear to me. So the psychophysical twist here is that these facial expressions have been randomly generated. So they haven't been hand selected by me or anybody else. So the random facial expression on the left happens to correspond to something that you know, for example, disgust, where the one on the right doesn't correspond to anything that's familiar to you. So using this bottom-up approach of using the perception of individuals, as we have just done here, we can identify the face movement patterns that convey meaningful emotion messages to individuals within a culture. Okay, so how did we generate these facial expressions? So we use a dynamic face movement generator developed by you and colleagues, comprised of a library of individual face movements called action units. Each action unit was captured from a real human, specially trained to move each one on their face independently using a stereoscopic system. We can also control the movement of each action unit using 6 or more temporal parameters, such as acceleration, amplitude, and peak latency. So by activating and combining different action units together, we can create almost any facial behavior. So during the experiment, we randomly sample a subset of face movements and assign a random movement to each, represented here with these color-coded curves. They are then combined to create a random face movement. The participant then categorizes it according to the 6 classic emotions, for example, if and only if the face movement pattern corresponds to their prior knowledge. Otherwise, they select other. This means that on each trial, we can capture the specific dynamic action unit patterns that convey these emotions to that person. And after many such trials, we can then build the statistical relationship between the dynamic action unit patterns presented on each trial and the participants' responses to produce a mathematical model of each facial expression. Importantly, this means that we have a precise quantitative representation of each facial expression that we can then formally analyze and compare across cultures. We also compute models for each individual observer to estimate population variance and to demonstrate replication of results across N participants. Specifically, each resulting facial expression model is represented as a binary vector that details the action units that are significantly associated with perception of the emotion. Each action unit also has corresponding values that represent their movement. This means that we can identify similarities and differences across, for example, different emotion categories or across cultures. For example, you can see here that surprise and fear share the eye whites, with a smattering in anger too. However, surprise and fear differ on brow lowerer. This action unit is shared between fear and sad. In contrast, lip corner puller is almost exclusively associated with happy. So by using a data-driven perception-based psychophysical method to derive quantitative representations of facial expressions, we can specifically identify what face movements transmit what emotions to whom, and to start to crack the code of facial expression communication. Okay, so having now covered the second point, I'm now going to show you some examples from our lab where we have used this data-driven psychophysical method to advance understanding of facial expressions beyond traditional boundaries. And we've done so in several areas, including emotions, a broader range of social messages, including pain, personality traits, and different smiles, and in fundamental signaling such as valence and arousal and superstimuli. We've then used these results together to build a formal generative model of social face communication. So today I'll focus on 4 main results on emotions, primarily relating to cultural differences and temporal dynamics. And before I begin, I should reiterate that these results relate to the perception of facial expressions, and some of you might be most interested in the production of facial expressions. So I present these results with in mind the intrinsic link between production and perception, the specifics of which continue to be investigated, For example, what is used for perception by the receiver is likely a subset of the information that is produced by the expressor. Okay, so let's start with the cultural variants that we've observed in our models of facial expressions of the 6 basic emotions. So this video is playing on a loop and it shows happy, disgust, and anger with East Asian models on the left and Western models on the right. So let's start with the East Asian models. You'll see here that the eye movements vary across these emotions. So let's see, happy, disgust, and anger. Do you see how different the eyes are here? So disgust and anger are very easy to distinguish just from the eyes because there's enough expressive variance there. Let's look again. So we have happy, disgust, and anger. They're very different. So now let's look at the Westerners. Happy, disgust, and anger. So you can see that you can't really tell the difference between disgust and anger from the eyes alone. There's really not enough expressive variance there. Now, if we switch to the mouth, we find the opposite pattern. So let's start with the Easterners again. Happy, disgust, and anger. So you can't tell the difference between disgust and anger from the mouth alone. Even the asymmetry is there. So happy, happy, disgust, and anger. They're very similar between disgust and anger. Now let's go to the Westerners. Happy, disgust, anger. So now you can distinguish them because the mouth movements are quite different. Happy, disgust, and anger. You can see anger is more of a pinching movement. So here, these data just briefly illustrate how we can precisely identify specific differences in face movements across cultures. Of course, I've showed you videos where we can observe these differences. Of course, we extract these differences using formal methods applied to the models that we derive. Okay, so now let's turn to cultural commonalities, because we're interested in both, of course, the cultural variants and the commonalities. So here we modeled the facial expressions of over 60 different emotions in 2 cultures. So that's about a 10-fold increase from the classic 6 emotions. And remember that each facial expression is represented as a binary vector. We then applied a data reduction technique to these models, these facial expression models, to identify any latent expressive patterns that underlie and structure this wide range of facial expressions. And results showed that 4, not 6, culturally common latent expressive patterns, each of which are associated with emotions with a specific valence and or arousal. For example, the leftmost expressive pattern primarily subtends positive emotions such as happy, pride, and delighted, whereas the rightmost pattern primarily subtends negative, high arousal emotions such as disgust, rage, and hate. Therefore, each of the 60 individual facial expressions of emotion can be expressed as a weighted combination of these latent expressive patterns. For example, ecstatic primarily comprises the wide-eyed and mouth expressive pattern plus a distinct accent from the smiling pattern. So here we found that 4 culturally common latent expressive patterns, each associated with valence and arousal, combine in an algebraic way to generate complex facial expressions. Okay, so now let's turn to dynamics. So facial expressions are dynamic, with different face movements activated over time to convey information. Now, given that our facial expression models are dynamic, we can examine sequences of face movements over time and to understand what information they convey. So using a combination of information theory and Bayesian classifiers and over 700 facial expression models of the 6 classic emotions, we found that their facial movements follow a specific temporal sequence where shared action units, such as the eye whites in fear and surprise, are activated early, causing confusion between these emotions, followed later by action units that distinguish them. Here, brow raiser in surprise and lip stretcher in fear. We also found this pattern for disgust So both transmit the nose wrinkler early in the signaling dynamics, followed later by action units that distinguish them: upper lip razor left and upper lid razor. Therefore, disgust and anger, both also considered basic emotions, are also confused early in the signaling dynamics and are not distinguished until later. So, keeping with dynamics, let's now turn to a recent study examining how emotion category information and emotion intensity information are transmitted over time. Using a similar approach, we identified the action units that perceivers use to classify facial expressions as one of the 6 classic emotions, represented here in green, those that are used to perceive emotional intensity, represented here in red, and those that serve a dual role of classification and intensification, represented here in orange. We then examined the temporal sequencing of these action units in each of the 6 classic emotions and found a clear temporal distinction between classifier and intensifier action units. So let me show you a couple of examples. Okay, so this video is a slow-mo video of happy. So you'll first see the eye whites, which for this emotion is an intensifier, followed by the smiling mouth, which for this emotion serves as a classifier. Okay, let's watch. So eye whites, then smiling. You can see they're temporally quite distinct. So let's go again. Eye whites and then smile. Okay, so let's now turn to another example in anger. So here you'll see that the intensifier comes later. This is the wide open mouth and the eye whites. The emotion classifier, which is the nose wrinkler, comes early. Okay, let's have a look. So nose wrinkler, then wide open mouth and eyes. Nose wrinkler, mouth, and then eyes. So again, you can see that these action units, the classifier and intensifier action units, are temporally very distinct. So here we've shown that face movements follow a specific temporal sequence, a syntax if you like, where emotion category information and emotion intensity information are temporally decoupled, presenting the observer with a cascade of socially relevant information over time. So this approach can also enable an understanding of the time point at which confusions might occur, for example, between different emotion categories or across cultures. Okay, so using these 4 studies as examples, I've shown how we've developed and used a data-driven psychophysical method to objectively model the dynamic face movement patterns that communicate emotions, including the 6 classic, and a wider range of nuanced emotions within and across cultures. And using results from our extended research program, we can now start to crack the code of facial expression communication. We can then build a formal generative model of face signaling that can be used to inform psychological theories and potentially the design of effective computing technologies. For example, in terms of a generative capacity, we've enhanced the social signaling capabilities of digital agents by improving how accurately they can convey emotion messages to human users in different cultures, appear more human-like, and have a wider repertoire of signaling capabilities. The face also comes in a wide variety of shapes, colors, and textures that can influence the interpretation of facial expressions. So having refined this approach with face movements, we're now applying it to 3D face morphology and complexion to derive a new synergistic account of social face perception, a face algebra, if you like. Okay, so coming back to our key points. The first is that facial expressions are not universal and are in fact culturally nuanced, which in turn can give rise to significant cultural confusions. The second is that knowledge of facial expressions is limited, in part due to the use of traditional theory-driven approaches. Third, these limitations have restricted the development of facial expression detection and generation systems and the ability of psychology to play a leading role in their design.
But as I've shown today, we're now at this exciting juncture where new technical and methodological developments enable knowledge to be expanded beyond traditional boundaries and to understand facial expressions in all their complexity, including what is cross-cultural and what is culture-specific. So finally, I'd like to leave you with some recent technical developments of the face movement platform, where several features have been added. So this includes different eye movements, we can also generate blushing and pallor, head movements in all directions. We can create superstimuli, of course. And more recently, mouth patterns to combine with speech. Thank you very much for your attention, to all my collaborators and funders. And if you have any questions or comments, please do feel free to contact me at this email address.
Thank you, Rachel, for the nice talk. And now is the time for the question session. So if we have any questions in the chat box. No. So we can post like the questions if we have.
So I have a question, if I may. So you were showing, just very interesting, the synthesized facial expression for someone from East Asian origin and someone who's Caucasian. So can you tell a bit more about how that was created? So is that something that is general, or are those some kind of averages, so average expressions, or do you see that with every instance of a facial expression, let's say, produced by an East Asian or a Caucasian subject? Because I assume you sample from some distribution, right? So what kind of expression was that? Some average expression for that culture, or?
So that's a good point. So what we do is we build a facial expression model from the perception of a set of individual participants in a culture. So usually we have, say, 20, 30 participants. Each participant does about 2,000 to 3,000 trials where they're categorizing these randomly generated facial expressions. What we can also do, of course, is that we can look at how consistent the facial expression patterns are within a participant. So you might be able to derive, say, one model, which is a good representation of all the trials, or you may prefer to derive maybe 2 or 3 models if the facial expressions vary a lot within a category and within a participant. Oftentimes what we find is that the facial expression patterns are within a participant are quite consistent. So we tend to derive a single model per participant. What we don't do is that we don't derive an average model across participants, because that would erase then things like population variance. So how do these signals vary within a population, even if the sample of participants we have are relatively homogeneous within the culture. So we derive individual models, individual participant models, so that we can demonstrate replication of effects across n participants. So we use population prevalence as a measure of that. I mean, it provides the reader with a bit more information about how these signals vary within a culture as well. Does that answer your question?
Yeah. So if I understand correctly, then the models that you showed for a subject of East Asian origin and Caucasian origin was basically derived from someone that was scoring the two. right? So
yes, so it's derived from perception. It's not derived
yeah.
from people making facial expressions. So we randomly generate facial expressions. It's totally agnostic. And then we ask people to interpret those facial expressions. Then we can build a model from the patterns that they associate with a given label.
Okay, interesting.
Okay, so we have, yeah, sure, go ahead, go ahead.
Yeah, I have another question, if I may. So one point that you made, it was really interesting. So it's very difficult to find common patterns across all cultures, and so there are some commonalities, as you said, but there are differences across cultures. So how much hope is there, let's say, for people to be able to build universal computational models that would generalize to the whole population? So does it have to be culture specific, or can that be solved just through data or some attribute analysis, or what do you think about that? So for example,
yeah, that's another good question. I think it depends on the level of communication. So what we're finding so far, and that has been shown in other ways in the literature before, is that you can have a certain level of understanding probably across all cultures. So something like what's negative or positive. So you can have a general understanding. Negative and positive usually is pretty good. You can get by on just that basic distinction pretty well. And what we find is that some of the face movements that indicate positive and negative valence are very similar and understood in a similar way across cultures. When things start to degrade is when you have more and more nuanced social categories. This is not a universal rule either. There are some nuanced social categories that are very easy to understand across cultures, and others which are quite basic, what we would consider to be quite basic, which are quite different. So a set of results I didn't show you today is on facial expressions that we use every day. So we have a lot of study on facial expressions to do with emotions like disgust and fear. We're not using these type of facial expressions, hopefully, on a daily basis, but rather we would use conversational facial expressions like interested, bored, confused, much more regularly. And so what we find is that the facial expression patterns that convey interested in East Asian and Western culture are almost identical. So they're very, very similar facial expression patterns, and they can be recognized in the other culture. So you can express interest and be understood across different cultures. In comparison, which is a bit unfortunate, is the facial expression of confusion. Now, the facial expression of confusion in Western models, the lips are pulled sort of laterally. In the East Asian models, confusion is more of a wide mouth gape. And so that's just one difference. It's just a difference in the mouth, but it's a big difference such that it actually causes confusion across cultures. So when Westerners are trying to interpret the confused facial expression models from the East Asian culture, they know it's not good, but they don't know exactly what it is. And it's also the same in reverse. East Asian participants know that it's not good, but they don't know exactly what it is. So it all really depends on what kind of level of understanding we want to go for, and also which complex and basic categories share the same movements and which ones don't. And that's really what we want to achieve with this project.
Okay, interesting. Thank you.
Thanks.
Okay, we have another question in the chat box from Albert. So if the facial expression analysis is so difficult and vague, do you think that across psychology literature, there is a significant impact of misinterpretations of facial expression? I'm not talking about just automatic analysis, but also just interpretation of expressions by psychology and psychotherapists, especially taking into account the confirmation of bias, which we know is vicious in interpretation of complex stimuli.
So maybe I can add a few things here. What I mean is Ekman's research has influenced the generations of psychologists who then relied maybe on facial expressions in their interpretations in the production of their results. And if we now undermine these assumptions, does that mean that some of the literature findings are perhaps incorrect or biased, or and then can we develop computational tools to address these problems?
So I would say yes to all of that. So the first point really is, have these results influenced researchers a lot in the direction, and they're thinking about the question, how to explore these questions, and also the research direction? I would say absolutely they have. And in fact, if you really look at the literature in detail, you can see that there was a big movement towards understanding universality. There was a lot of other people looking at cultural differences, but they're kind of sidelined a bit. And the main focus was on universality. And at some point it was, oh, we have these 6 basic emotions, they're universal, let's all just go home. There's nothing more to see here. And so we didn't really have a lot of development in looking at cultural accents and things like that, because there wasn't really a big impetus to do this. So that's one way that it's influenced. Another way that it's influenced people, researchers in psychology, the general public, and also in other disciplines, is the same point, is that the general message is one that has been sort of simplified, and that is facial expressions are universal, let's just move ahead. There's nothing more to see here, let's just use these 6 facial expressions. People within the field itself would argue that's not really true. The messages get simplified over time, but nevertheless, that's what people received, and that's what people used in their own work when, say, for example, designing automatic detection technologies and so on. They're very much based on Ekman's 6 basic facial expressions of emotion, which are theory driven. They're chosen by experimenters, they're not data driven. They are Western sampled, and they are static, and they're recognized primarily by Westerners. There's only 6 emotion categories. So again, it's very limited, and this has impacted other fields for sure. Now, what you're saying is, can we overcome this? And I would say, yes, we definitely can. And this is again, another goal of the research program, and that is to go beyond the traditional boundaries of facial expression research. You're going beyond 6 emotions, going beyond emotions, adding dynamics, and then really committing to understanding cultural similarities as well as the differences, so we can have a proper understanding of non-verbal human communication using facial expressions. We use them all the time, and we don't have a formal understanding of them. That information then hopefully will be used then to inform, for example, the design of socially interactive digital agents, because at the moment, if they just have Ekman's facial expressions, you're not going to sell these things in East Asia very well, because they don't recognize them. They recognize some, but they don't recognize them all. If you have a conversational agent, it doesn't have any conversational facial expressions. It just has fear and disgust. So this is a secondary goal of the research program, that we can develop a generative model of social face signaling that's culturally sensitive and socially sophisticated, that can then be used in other technologies.
Yeah, well, you can also extend this obviously to other signals. I mean, you don't have to stop with the facial expressions. You can add gestures, you can add body. So then the next question is, do you think that all our computational approaches necessarily oversimplify human behavior? Because in order to represent behavior concisely, we need to have a clear abstraction, and that goes through simplification in most of the cases. I mean, if you look at body pose representations, most people use open pose. It's just a skeleton, you know. It has limitations, and then we start with very simple representations, and then we try to make them more elaborate. But at one point, we stumble upon computational requirements, you know, data explosion, etc. So we're still not very good in abstraction. And as you say, maybe this is also affecting the way we approach the problem. We are looking at more and more reductionistic problems, so, you know, just classification instead of a true understanding. Do you think computational approaches are adversely affecting psychology as a field?
So I think the computational approaches are adversely affecting psychology as a field. I would say probably no, but I would agree with you with respect to this desire for simplification. Of course, this is what we want to do, is to have an abstraction and to have an efficient model of signaling, for example. But we only really know whether that's sufficient until we go beyond that, right? Until we sort of look at more complex signals and whether they can be reduced to whatever. And that really requires, you know, adding body movements, hand gestures, and so on and so forth. So I think the main limitation at the moment is and I agree with you, is really one of a sort of technical limitation in the sense that we have face movements. These are very complex, but we also have head movements. We have viewing distance. You have problems with like transmission over channels. You have body movements, body size. We have this massive information space that we would like to, in principle, sample from to build these models. But that's not tractable. There's no way that that can happen. So rather, the goal would be then to examine each information source in isolation to build models, and then combine these reduced models from that more complex information space with the idea, with the understanding, of course, that when we model signals from a particular information source like the face, we're not saying that that's the end. We're saying that we've got these models and that we then want to be able to combine them with say body movement models to understand how they combine together and interact for social communication. So I think that it's like really a case of making something tractable by focusing on one thing at a time, and having the view that no, we're not at the end. We're very, very far from the end. We also have voice, we have context, we have all kinds of things. And being patient with that. Does that answer your question?
Thank you. Yes.
So if we have any more questions, if not, then I have a question. It's like, can we like simplify maybe like the number of category of emotions, like let's say like positive emotion and negative emotion, and maybe that can simplify like this biasness, because like maybe for some application, not for all, of course, like there, like depending on the applications, we need to maybe simplify the emotions. And can this be one of the way? And it could lead to like debiasing the situation.
Yeah, I guess I think it all depends on the purpose of the exercise. So if you have if you want to build a system that does something very basic, then positive and negative is probably a reasonable distinction to make. It's probably reasonably universal and so on. Just as a kind of aside, the main difference between negative and positive is that there's many more different types of negative signals. So negative signals vary much more than positive signals, probably because it's more important to avoid negative things and you need to know what kind of negative it is, whereas positive is good, but you don't have to rush to avoid it or whatever. So I think it all depends on the purpose of
the ground of application.
Yes, exactly. And then things will be more or less difficult, I guess.
Yeah. And I think another important thing like is like for a micro expressions, like where we have like very minute, like less time of expression, then like it's more challenging. So what could be the direction, like, do you think in that point, like in a micro expression scenario?
So I guess the challenge with micro expressions is that they're small and difficult to detect unless you're at sort of close distance and so on. So, I mean, that's kind of the main challenge. Micro expressions are very salient to human observers, and we can identify the specific face signals that human observers will detect in a human face. And the human visual system, of course, is totally designed to do these things, and it's excellent at doing it. With more automated systems, it's a bit more tricky, especially when you have noise in the channel, or simply if the face is too small.
Right. So if we don't have any more questions, so we'll thank Professor Rachel Jack and for its nice talk, and let's like with the round of applause. Thank you.
Thank you very much. Thanks.
So after this, we have our next keynote, which is the keynote 2.
Yeah, so the next keynote starts in 5 minutes. So I propose we take a short break. So if someone needs to fetch a glass of water or some other errand. And let's start in 5 minutes, but I would encourage everyone to, let's say, turn on your camera, chat a bit for the 5 minutes, and then we continue at 6 o'clock local time with us, and so at a full hour.
Yeah. Yeah, like we are going on time.
Yeah, so we are perfect on time. It's to the
Yeah.
minute.
Yeah.
Yeah.
I tried to make a poll about where our participants are joining from, and I didn't manage to do it. So I'll do a simple version. I'll just post on the chat window the continents, and you can like the continent that you're joining from. So let's do it this way. Let's see who is burning the late hours.
I got my glass of water.
Apparently there is no commenting on the chat, so that was a bad idea. Okay.
So is that disabled or?
I think it's not enabled. I mean, for some reason, this is, well,
Yeah, I
if
think like it's enabled.
I don't know whether I
Yeah.
can enable this by going to the preferences.
I see some comments, so I guess it's
Yeah.
it is
Yeah,
working.
comments are
Yeah.
coming. Yeah.
Okay, so my time tells me it's 6 o'clock here. So maybe let's proceed with the program. So it's my honor to introduce the next speaker. And I'd like to thank you again, Mohammed, for accepting the invitation to hold the talk. So I have a short CV printed out just to introduce the speaker. So Professor Mohammed Chetwani is a full professor in signal processing and machine learning for human-machine interaction at the Institute for Intelligent Systems and Robotics of Sorbonne University. He is part of the PYROS research team, and his activities cover social signal processing, social robotics, and interactive machine learning with application in psychiatry, psychology, social neuroscience, and education. He is the Deputy Director of the Laboratory of Excellence Smart Human-Machine-Human Interaction in the Digital Society. Since 2018, he is the coordinator of the Animatus H2020 Marie Skłodowska-Curie European Training Network. He is the local co-chair of the IEEE ICRA 2020 and the program co-chair of ICME 2020. Since the same year, so 2020, he's also the chair of the Ethical Advisory Board of Sorbonne University. So Mohammed will deliver a very interesting talk, I hear. So I give the word to you, Mohammed. So please go ahead.
Thanks for this introduction, this kind of introduction, and thanks for the organizers for inviting me. Maybe I can start by sharing my screen, so you let me know if it works. Should be fine. Is it fine? You see everything? It should be fine. Okay.
Yes, we see the screen.
Okay, great. Okay, so I'm working on as Peter was saying, on human-machine interaction and human-human interaction. So far I've been interested in several parts of it. So part of the agents and the human behaviors. But today, what I will try to show you is some of our recent works about social learning agents. So, and in particular, I will focus on the role of human behaviors on that. So how human behaviors, I hope that it fits much better the topics of this kind of workshops. And so I will start probably to define the situations that we will be targeting here. So the situation that we have is here in the bottom. You have the figure. You have agents. So artificial agents, we mean by that artificial agents that are learning with human teachers. And the assumptions that we have here is that humans and the agents are sensing and acting in the same environment. So this might be a strong assumption, but we are facing that in several situations. For example, Vito was mentioning one of our projects that is called Animatas, so where we are discussing about educations. And in education, you have this situation where you have humans and agents, mainly robots, but also virtual agents, that are, let's say, sensing and acting in the same environment. Of course, there might be different skills. I will discuss that later on during the presentation. I will show you that this might be have an impact because, of course, humans and agents might have different skills in terms of perception and action in the world. So the objective of this situation is that it's called learning from human teacher. Sometimes you find also other terms like interactive task learning. And the idea is really that we have a process by which an agent will learn to communicate about the task. So this is really important for us because we need, for example, agents to help humans, but they also probably need to have communication for their own needs, like if they have to perform some task, they probably need also to collaborate and coordinate that with humans. And they need, at the end, we need humans. We need humans that can collaborate with this kind of agents, and you can imagine in different situations. So I will not show that here, but we have been working also in industrial situations where you have robots that have to learn to perform some tasks with humans. Just to show you what are the differences and the context on. So I'm taking this picture from some works for Amish and this reference here. And what is interesting is that they try to show what will be the difference between, let's say, traditional machine learning techniques, where you have, of course, algorithms, but you also have users of this kind of technologies and machines or these AI systems, but you need also experts to design them. And most of you are also here in terms of experts. So we design the machine. So there are a lot of things to do, and all the stuff that you have to do when you have to design these kind of machines. And then if you look to the change of the models and how we interact in some way with these machines, we have kind of cycles that are quite slow in some way. So you typical things is that you set up some design parameters, and then you have some data, and then there is also the annotation problem and all this kind of stuff, and then you put that in a machine, and then you wait for the training, you do the evaluation, and then you update the stuff. In the interactive machine learning process, this is really different. Here, first, you don't see explicitly the expert. It doesn't mean that there is no need for expert. There is a need for expert to design that. But for the interactive machine learning, the user is interacting directly with the machine, and you have very short cycles in terms of updates. For example, I will show you examples during the presentation, but what is well, you can give labels, you can give for example feedback to the machine, and this is this makes the interaction much faster. Doesn't mean that the convergence is faster, but at least you have a kind of simultaneous development and usage of the machine, of the AI system. So there will be a lot of questions around that, and I will try to focus on some of them. And one of the questions is what will be the impact of the user. We see that this is might be very interesting, but one of the questions is that the user will have directly an impact. So if you have good users, expert users, maybe or users that are not experts of machine learning techniques, what will happen on that? One situation that we are facing is that most of our users in some of our applications are children. So what will happen if you put children in front of these machines? What will be the impact of your systems? So the work that we are doing is a work that we did in Animatas, but also in other projects. Is the focus on what we call teaching signals. So the human teachers is providing teaching signals that might be very multimodal. So we had just about facial expressions, but you might imagine also signals like gestures, pointing is a kind of this, but speech also, verbal instructions, and they can have also different kind of forms. This might be a feedback. I will show you some of the ways of doing that. So feedback is more the learning agent is doing something, and then I can give a feedback. And you can imagine that after that, there might be also techniques to learn from that. You could also demonstrate. This is also something that is interesting in this kind of loops, interactive loops, when you don't know exactly or how to do it, how to explain it, but you can show it. This might be also interesting. Instruction is another form of interaction that you can have. Of course, this you can combine them. One of the challenges is trying to combine all these kind of forms of interaction. They might be more or less informative. They can be very explicit. They can be also implicit. They might, but all of them have the intention to shape the agent behaviors. So the idea is that the human teacher in some way wants to change the behaviors of the agent to reach a certain goal. So one of the questions is how an agent can use this kind of teaching signals that might be very diverse, and how you can exploit them to use all this kind of stuff. And one of the point is that usually in machine learning, you expect to have a lot of data. Of course, when you think about this loop, you cannot imagine to the human teacher to provide as much as you want in terms of signals. So you have to make sense from few data, and it should be really interactive. So some ways of doing interaction. There are other ways. You can find a lot of ways of doing interaction, but these are some traditional ways of using having human in the loop. So you have the standard imitation learning. So A is for actions, and S is more for states, and this is for the task. And in the standard imitation learning, so A is the agent, and here you have the environment. So you have the human. And in the standard imitation learning, what you try to do is you see a human that is performing some actions, and what you try to do is to do the same actions. You try to do exactly the same. You can have also evaluative feedback. So here the agent is doing something on the environment, and the human is perceiving the actions and the state and just providing feedback, saying, for example, that was good, that was bad. You can also learn from observation. So here, for example, in observation, you just, so there is no explicit teaching. So you just observe something. And I will show you also examples about it. So most of the works that I will show you is about evaluative feedback and imitation from observation. And the last one that is also interesting is it's something that we are also doing is learning attention from human. So there might be a lot of things to do in the environment, and not all the stuff are important. So trying to guide the attention of the human is something that is important for the interaction. So just to show you the kind of examples of the role of humans in this kind of stuff, this work has been done by some colleagues in from McLeod, and they have been doing very interesting works about human strategy. This is a very simple task when you have to classify different kind of objects. So you see different kind of pictures, and the scenario was very simple. You have just to show to the robot objects that you can grasp and others that you are not grasping. So if you think about machine learning, this is a kind of a very basic machine learning task, because this is a binary task. You have to define a threshold, and from the threshold you have positive and negative. And when you look in the strategy of the humans, when they do that, the colleagues, what they found, it's quite interesting. They found different strategies. So they summarize that in three kind of strategies. One that is called extreme. So here the extreme means that you show positive and negative, but only the extreme ones. Okay, not really around the threshold. The linear is they found different kind of linear, one going from the negative to the positive or the positive to the negative, but you start from one part of the word from negative, for example, and then you give examples, and each time you give, of course, the label, and then you move to the grasper. And you have also people that can provide only positive examples. And this makes sense because we ask people, here the people will ask to teach what is graspable. And for humans, a natural way is to teach something that is positive. And it's very rare that we teach things that are negative, for example. And this is only one example, and there are a lot of examples in the literature showing that the human strategy is not really fitting what we have in mind in terms of artificial intelligence, and we know that, for example, that we need negative examples and positive examples, and this is something that we should have in mind when we design these kind of models. So what I will try to show you today is kind of modifications of nonverbal behaviors during what we call social learning. So social learning is really about is a process where we have so it's not specific to machine learning. It's social learning is something that we have between humans, and it's a natural way of learning. And you have a kind of individual that we can call the demonstrator. The term is not we will see that this might change during the talk. We might have also just people doing actions, not necessarily doing explicitly demonstration, and they try to influence in some way another individual that is the observer. So you see the kind of interaction that we have. We have a kind of someone doing something, and you have the other that is observing. And the idea is that we increase the priority that the observer learns. So we should have that in mind when we design these interactive models. But the influence means that people could change. And one way is to use nonverbal behaviors, and I will show you examples of when people are facing this situation of social learning, they also change their own behaviors. So why we need to change our behaviors? For example, to show actions that leads to required goal. So this is something that we usually do. We change our actions when something is important. We show it, or we try to show it to the human, to the observer. We can also show the goal. So we have there is a literature showing that humans, when they want to highlight to for example, to children a goal, they can really highlight by nonverbal behaviors, for example, by speech, prosody, but also gesture and movements. We can also highlight, for example, relations between actions and outcome. So, for example, you really show that sequence of action will give this kind of outcome. So in the kind of robotics that we are doing in my group, so we face a lot of situations where we have humans in front of robots, and we want to teach them new actions. So we have different ways of doing that. And here there are some examples. For example, the first one is the local enhancement. So you want to refer to an interest in particular location. So you can imagine that you have a lot of objects, and you want to say, okay, this is the stuff that we are interested on. So instead of looking to all the signals, all the locations, you try to focus on something. You can have a stimulus enhancement. So this is similar, but the idea here is that we change the interest in some of the actions. I will give you one of two examples right after. And this is known in the communication with what we call ostentative stimulus. So it's voluntary actions to attract, for example, the attention of the observer or the partner. And this is really about communicative intention. And most of the works that I will show you right after is about it, how we can change and how humans change their intentions in front of agents that are learning. And this change will make a lot of troubles in some way. So these are examples of this kind of troubles. There is some works that have been done, for example, in what we call acoustic packaging. So in this work, you have an adult that is showing objects to children. And what we found in this kind of work is that when you do a movement, when you try to do the movement and you use the prosody, this is kind of synchronized. And this kind of synchronization that is called acoustic packaging is interesting, but you should not try to replicate that. What is important is that in the way of the synchronization, you try to highlight something that is important. What is important is not the fact that you have the speech and the specific prosody of the movement, but the synchronization is in some way, okay, telling to the other, okay, now you have to look to that. The rest is not important, but what I'm showing right now is important. Another work that was quite interesting is a very simple task here. It's the difference between doing and showing. So there is a very simple maze. So you have a starting point and the goal. And what we have been doing in this work is that you have safe colors, so safe spaces, paths where you can go, and others when you cannot go. So when you ask people just to do it, okay, you ask people just try to do it, they go and try to do it, and there is no notion of trying to interact or to observe, and you have no notion of observing. Now, if you do the same thing and you ask people to say, okay, you have to show it to someone else, and from the demonstration, people will understand what are the safe or not the safe zones on the maze. So if you do that, you see the behavior is changing, and that's quite interesting, because if I'm learning from the doing or the showing, the doing is fine. I will learn to do it. But if someone is showing me something, this exaggeration of movement, it's not useful. There is no need to replicate that. And in the same communication channel, you have two things. You have the task that is done, but you have a communication on that. And that's my point here, is that probably what we should do, and it's something that we are doing in the lab and we are proposing, is that the vision that we have on that is we need a kind of a translation between the teaching signals and the learning agent. And this translation is called the interpretation phase. And we want to understand the intention of the humans. Was the intention to do the task or to communicate something else? And by doing that, to include explicitly interpretation phase, we will try to infer the best information that we can get from the teaching signals to get the learning agent to do that. So this means that sometimes the teaching signals that are provided by humans are not really useful directly for the learning agent. So we have to filter them or to transform them. And transforming them means extracting information that are useful for the task and separate that from the communication. So first, one example of that, what we can do. One thing is trying to, it's a traditional task. You have a task that is a sequence. For example, you need to go from the box blue and then the green and so on, the pink and so on. So you have a sequence, and the robot has to learn that. Of course, the agent, you can imagine to do that autonomously. And this is the traditional framework for doing that, is the reinforcement learning framework. I will not go probably into too much mathematical details, but the idea is you have states and action, and you have a reward function. And the reward function is there to tell you, okay, if you do well the sequence, you will get a reward from that. But what we want to do, so this could be done autonomously, but we can have also a human teaching or trying to help the robot to do that. And the assumption is that if we have a human that knows the task, he knows the task, so he will try to help the robot to do it faster and more efficiently. So here what we provide is an evaluative feedback. So evaluative feedback, if you remember, was I do the action, and then the human is saying yes, no, it was good, it was bad. And here what we do is we also provide labeled instructions. So instructions, for example, for us, instruction could be pointing, but it could be also verbal instructions. Here in this work, we have been using only gestures, different kind of gestures, but you can imagine also to use, we don't use too much speech for speech recognition problems mainly, but we have been using that mainly also. So we call it unlabeled instruction. Why unlabeled? Is that because we need to interpret them. We need to interpret them and to put a label to them. So the idea is that we have some gestures, and I don't know, the robot doesn't know the meaning, and it's perceived that, and then from that I will try to get the label. So how we do that? So on the left you have the standard reinforcement learning approach. So you have states, and you can try to get the actions, and from that you have you can use different kind of reinforcement learning techniques, the ones that you might prefer for doing that. There are different kinds of techniques. But on the right is what we have been introducing some years ago, is that you have states, you have actions, and what we have been doing is that the instructions, they have been used to, the instruction, the idea of the instruction is to shape the behaviors of the agent. And for that, we added interpretation. So you have the instruction, but from the instruction, when we start, we don't know what to do with it. And what we learn is to perform the task as we do for the standard reinforcement learning, so going from states to actions, but we will also learn the communication, so the interpretation of it. So how it works. So here it's one of the architecture that we have been doing. And you will, so the idea is to have the, it's called TICs, and this architecture is task, instruction, contingency, and shaping. So the task, so it's based on several models. So each of them is learned by reinforcement learning. So we have a traditional task model that learns from a reward from the task. You can have evaluative feedback from the human. And then we have the instruction model. So the instruction, you can, it learns to interpret all the signals. So from that, we have the instruction signals, and the contingency model is basically, it's a very simple model that learns to associate task states with instructions. So the basic idea is very simple. So you have a task model that learns a task, instruction model that learns to interpret, and the contingency model is just learning the relevance between the task state and the instruction. For example, I have a pointing, and the pointing says that you have to go to the pink box. And the robot, his wrong in interpretation is going, for example, on the red or the blue one. So this is a wrong interpretation. So what you will do is to update the models by that, because the human will provide a negative feedback right after that. So we rely on the human to help the agent to check the interpretation and check also the task. So one thing that is important here is that we shape the component by the task and the instruction. Okay, so we interpret the task, we interpret the instruction, and then we can decide about kind of action. But as you could see here, one thing that is important is we rely on the human to provide information about the task and the instruction, and the robots or the agent will learn both of them. But the human could be non-optimal, and this is kind of stuff that is challenging in this kind of works, is how to use humans that are non-optimal and how we can be robust to that. Okay, some results on that. So here it's a kind of what we call the probability to converge. So the idea of the convergence is that you reach all the goals of the states, so you are able to do the task. And what we have been doing is trying to simulate the probability to have an error. So the human can make some mistakes. So here you have the probability of making some mistakes. So 0 means that you are optimal. So the human is optimal. So you have the reinforcement learning plus different kind of techniques to combine the interpretation. And what you could see is that when the human is robust, the system is, the human is not making mistakes, so we are able to learn. But when the human is trying to make some, is making some mistakes, till, for example, the green one, so it's half of the time you are making some mistakes, the system is still robust. Of course, when you start to the majority of the time you are making mistakes, now the system is not able to learn. So this is something that is important to have that. So we are able to learn with this kind of interpretation from non-optimal human teachers. Of course, if the human is fully always wrong, you cannot learn. You need to have some tasks and some goals and states where the human is able to do that. So other ways of learning is learning from the observation of non-optimal human teachers. And here it's a similar task. You have to perform actions in the word. So it could be a sequence. For example, you have to take the key to open a door. So you can do a lot of actions in a word. But here, what we have been doing is learning from observation of a third-party agent. So you see someone in the same environment as you. He's not explicitly teaching, but you see the agent doing actions. Okay, just doing some actions, as children can see, can observe someone else doing actions, not explicitly teaching, but just by doing that, you can learn from them. So here we try to combine different kind of strategies. The first one is autonomous learning. So it's traditional AI-based systems when you have a reward. So you get a reward just by being able to do the action. You can do imitation learning. So you can try to reproduce the third-party actions. And then something that is important is, as you now you understand, is to ignore some of the actions. So for that, we introduce curriculum learning. The idea is that sometimes I have to switch from autonomous, trying to do it by myself, or trying to imitate the others. And this might also depend on the way, on the complexity of the task. So this, I will not show you all the scenarios, but some of them here. So here, there is a very simple scenario where you have 6 objects of equal difficulty, so you can manipulate them, and you have the global competence, and this is the competence of manipulating objects from the agents. So when you have no demonstration in red, means that you are doing only autonomous. So you could do it, but it takes time. Then there is demonstration only for 3 objects. Okay, so of course you learn faster than no demonstration. When you have demonstration from all the 6 objects, of course you are learning much faster. So this is what we were already expecting, is that if you add demonstration, teachers, we are already able to learn faster, and it might be more robust. But the thing that are important for us is what is happening if now we are not optimal, or we try to get some optimality in terms of objects. So what you have on the bottom here is that an agent that is trying to learn from different kind of objects. And what is happening is that you don't have the order, and the system don't have the curriculum learning, so it's just learning randomly the objects. And at one point, the system is easily trying to get the first object because it's quite easy, and then it's making a lot of time to master the other objects because they are difficult for that. And on the bottom, what you could see is that the competence for the objects, but now you have a human that is giving you the right order. So so showing the easier one to the more difficult ones, and you just have to follow the order. So instead of trying all the objects at the same time, you just filter the intention of the human. That is, you take an object and you go to another object and you master it, and from that you can move to another object. So in this way you also infer the intention of the human that is going to easier to more difficult. The last example is that of course we observe the human, but what will happen if we have to ignore the signals from the human? So we introduced for that what we call trust-based interactive reinforcement learning. And the idea is that you have the interpretation phase. So you have the teacher providing instructions and feedback. And instead of going directly to the reinforcement learning agent, we try to see if we can trust the teacher in terms of that. When we say trust, there are a lot of literature on trust, but here in some way it's about the competence. It's about how we can check if the human is providing the good examples for the agents. So how we have been doing that. So this is the best architecture. So basically, the architecture is relying on what we call the teacher state action value model. So in terms of to make it very simple, the basic idea is that we try to infer from the instruction and the evaluative feedback, and mainly the evaluative feedback, 2 policies. One is the real policy that the robot is doing, and H is the policy that we believe that the human will do on that. And we have been trying to, so in some way we observe, and from the observation we try to get the distance to check how far we are from the expectation of the human. So you try to predict what will be the policy, the instruction of the human, and if they are wrong, they are not fitting your prediction, your expectation, you will decrease your trust on that, and in some way you filter the actions. So we have been doing that in a very simple task. It's again a maze. I don't know if you see that very easily, but you have a kind of optimal path on the maze. So it's quite complex in some way in terms of maze, but we want an agent, we want human to teach the agent to the optimal path. But what we introduce here is different kind of regions. You can introduce regions where the human is not good, and you can also introduce regions where the human, you could have different teachers. There are different scenarios. I will focus only on one scenario. So in this scenario, you have two kinds of teachers. You have an expert teacher. So when we start, we have very expert teachers, and when and after we don't have this kind of teachers. So what we have been doing here is to check where we can ignore the human, and it's what is happening here. So you have expert teachers. You you try to learn from them each time. You try to learn from them, and you can have different of spacity, like what we said about having all the signals or not. And then when we start to have non-expert teachers, we don't rely on the we start not to rely on the human. And of course, this is dynamic, so you can also after go to the expert teachers and so on. So this is just an example of scenarios. There are other scenarios. Okay, so just to summarize, what I wanted to say is that we are so there are a lot of situations where we don't have experts to teach humans, to teach agents, and they will have a lot of impact on the learning. And here I show you only some ways of dealing with that, and there are of course a lot of challenges, like how we can combine different kind of teaching forms. I show you only about instruction and evaluative feedback, but of course when you have humans, and it's what we see in education, for example, is that you try to manage or to use different kind of signals, and humans are relying on that. So there are still some questions like how to learn from very few data, how to ignore. I show you examples there, but this kind of phase of interpretation is really a loop, and we really rely on this kind of loop of interaction. And there is the question of transparency, because you cannot really ignore without communication, and transparency is, and explainability is one way of doing that. Okay, so thanks for your attention, and thanks for all the colleagues and students that shared all this work, and thanks for your attention first.
Thank you, Mohammed, for the interesting talk. So I open the floor for questions. So of course, virtual claps. And if anybody has some questions, just let me know. Okay, Albert, please go on.
Okay. Thank you very much, Mohammed, for this talk. I have two related questions about how we look at human learning when we try to model the agent learning. And the first one I want to ask is, during human learning, when we perform tasks, we sometimes cross junctures where we take one of possible paths, but then we retain these key points and turn it into learning experiences. For example, let's say I look at the sky in the morning and I decide not to take my umbrella, and then I get completely wet. And the next time I look at the sky and see a similar cloud formation, then I will take my umbrella. So I basically store that moment. For me, it's a potential learning experience, and I later fill in this information. So I create a proxy, if you want. And reinforcement learning does not explicitly propagate such stored moments, right? Some intrinsic motivation-based models can potentially include explorative action selection in the form of hypothesis testing, but this is also not very commonly done. Now, you showed us a couple of models, for example, the TICS model. Would that model be able to incorporate this kind of reasoning? And or which of the frameworks you have shown us would be ideal to store and propagate such information?
Yes, that's a good point. I did not really mention directly intrinsic motivation, but when I said, for example, learning from observation, in the click architecture, where you have just to observe, you can imagine that you can have motivation just by observing the others. That's important for you, and intrinsic motivation is something that we are putting in the models now. Actually, not necessarily in TICS. We have other models now, but this is kind of stuff that we are trying to put that. Last year we did some work on that with a model that is called Curious, and is basically on this idea of trying to get the curiosity inside the models. So that's one way of answering the question. But the other question, the other point is more if the models that we have are fitting what we expect from humans, and this is there where we want also to combine different kind of forms of learning, and this might be very difficult, because usually it's easier when you try to design. When we say we have experts that are designing parameters and so on, it's easier when you have that. But when you try to face, let's say, different kind of learning situations, you might need different ways of learning. And stopping learning, for example, it's a question. When you stop to learn from something, and why you should now start to learn again. And it's why we introduce the curriculum learning. But the difficulty is that it's till now useful to stop something, but not very efficient to start again to learn, because it's for example the umbrella that you just said. I'm sure if you go to another country, other place, you need to do something else to adapt that, and it's not so clear how we can trigger that, for example.
Thank you. Thank you. If there are no other questions, I will have another question, but I'll wait a moment. Somebody else.
Maybe a question from my side. So you were talking about active learning, a human teacher, and in the beginning you also mentioned multimodality. So
Yes.
if we as people learn, right, so we take in different cues. It could be gestures, it could be speech from the teacher. So in your examples, I think you mostly focused on gestures, right? The teacher, the human teacher, was showing some things to the robot, and then he was learning based on that. So where do you see the role of multimodality here? So is that just another means of conveying information, let's say through speech and gestures? So is it the same information, or can you extract more from that, or also the interplay of different modalities?
We use gesture basically because speech was in the context that we have, speech was not efficient, and there are a lot of situations. For example, the works that we are doing is in education. In classrooms, it's difficult to use speech, for example, but also with children with autism spectrum disorders, some of the tasks are used on this context, so you might be very difficult for that. So it's more a practical reason for not doing that. But in other situations, we are also using different kind of signals, like let's say gaze is important for us. It's something that we are using a lot. We used nonverbal signals, facial expressions, and speech, but more for detecting engagement. And then from that, we use that for the learning. So it's not directly something that we can use, but we have been doing that. But I'm sure, for example, the example of acoustic packaging, it's interesting way multimodal signals are useful to highlight something. And we have been doing that, for example, in prosody and gesture. They are synchronized, and here you extract really something because you have the two signals. Otherwise, you just see a gesture, you just see a prosody that is changing. But the fact that they are synchronized highlights something, and this is important to get that. So for sure, this might be more interesting to get the multimodal signals. But when it comes to practical applications, this is not so sure that we can take all these kind of signals.
Yeah, thanks. So any other questions? Albert, you had another.
Yes. So I'm thinking of how the fastest learning humans are able to transfer information from one domain to the other, mainly in form of abstractions. And in early cognitive science, this was achieved in modeling. This was achieved with meta models. For example, Susan Epstein had a model of, that trained expert agents in a domain, and then basically for that particular domain learned, a meta learner learned how to weigh the experts. And when this information was carried over to another domain, you basically left the experts alone, but learned how to listen to them, like which one is prioritized and which one is not. And with this, which is, if you think about it, very similar to a deep neural network, where if you do transfer learning, the early layers stay roughly the same, but then the later layers are adapted more to the new application domain. Now, you showed us, for example, this maze navigating behavior. And then I'm curious whether the learning there is about, is it about that particular maze, or is there something that can be transferred to different mazes, and or maze-like structures even, not just the same type of maze, but things that have similar structural properties?
Yes, we did that. And for that, what we for example, one question is that when I said that we interpret and we separate the communication and the task, we have been doing, for example, could we learn from a task, communication and the task, and then we transfer only the communication and not the task, and we adapt the task to another task, and it seems to work for kind of task. For example, if it's maze-like, you could do that. But when you change really the task, probably you need also to learn the communication and interpretation, because this is another way of communicating about the actions. But for the same kind of task, it seems to work, this idea of trying to rely on the fact that we separate the communication by trying to learn a representation of the communication and the task, and then you change only the representation of the task. For different kind of mazes, it was working for that. Now the question is that we want to have that for really different tasks. Till now we didn't have a clear answer on that.
Thank you very much.
Thank you.
Okay, so any other questions? If not, then I would like to thank you again. So
Thank you.
everybody, virtual claps to Mohammed for the very nice presentation.
Thank you. Thank you.
So we have a 15-minute break scheduled now. So till on my watch, it's till 7 o'clock. So 10 minutes left, and we start with the oral session after that. So thank you again, Mohammed, for joining the workshop and giving the talk. It was really interesting.
Thank you for your questions, Anya. Thank you.
Okay, so